Kia ora and welcome to this video on question 5 of the 2014 Scholl Calc exam. Again, two options here. The first one is a nasty differential equation which we're given the solution to, so fortunately we don't need to integrate it. Part B has a pretty random function which is a product of three things, and we're given some pictures that relate to the function and we have to answer a question about an area. And then the second option is an ellipse enclosed by two hyperbolas, and we have to find the largest area of an ellipse. So it looks like an optimization problem, but we will use the discriminant. Okay, so first part. As I was saying, when you're given the solution to a differential equation and we just need to verify it, we don't solve the differential equation by integration. It's easy to use differentiation. So the first derivative here, we've got e to the stuff, right? That I'm calling this whole thing the stuff. And when we differentiate e to the stuff, we get e to the stuff times the stuff differentiated. That little dash there is derivative and not a power. And one step further, the derivative of e to the cx is c e to the cx. Okay, so that's the first derivative. The second derivative, we now need the product rule because we've got f here and another function g there. The derivative of f, well, that's actually the original function, e to the cx. So f dash is just dy dx. Okay, we've already got this dy dx thing here. And so that's going to go e to the cx times ce to the cx multiplied by ce to the cx again. Okay, that there is f dash. That there is g, and then g dash f, c squared e to the cx multiplied by e to the cx. That there is g dash, and that there is f. So all we've done there is applied the product rule. Now there are some common factors in this. We can pull out e to the cx out of both terms. Okay, it's there, it's also there. We can pull out a c, and we can pull out an e to the cx. So, okay, with leftover stuff, we need another c e to the cx in the first term, and we need another c. No, we don't need another c. Because if we pull out c, I didn't see that little c there. Oh, that's a mouthful, I didn't see the c. Pull out c squared. Then we don't need a c there. And all we need on the last term is a 1. Okay, so that's the second derivative. Now look at what we're trying to achieve here. We're trying to make it equal to c squared times y times log y times 1 plus log y. So something like note that y is equal to e to the cx. So ln y is equal to e to the cx. So this dude here is ln y. This dude here is ln y. And this dude here is y. So therefore d squared y over dx squared equals y times c squared times ln y times ln y plus 1. And we've proven it. Box, smiley face. Not too bad. And hiding at question 5a. So often the exam gets harder as you go through it, but there's sometimes an easy question at the back, and we're just going to make sure we get to it. Okay, consider the function It's a multivariable function, f of x, y. We can think of this as z if you want to. So this dependent variable z depends on x and y, and it also has a constant in there a, which ranges from 0 to 1. And we're given the regions where the function is negative or equal to 0 for various values of a shaded in the figure 4. Actually that is wrong, because the diagram underneath the caption here says positive values are shaded. So, and then this one says less than equal to 0. So there was a mistake in the exam this year. But let's just have a look at which one's right. Is it the caption that's right, or is it the question that's right? First up, it asks us to describe how the boundaries arise from the solution to f of x, y equals 0. And then we're asked a question. So first up, let's have a look at what f of x, y equals 0 looks like. So if it equals 0, one of the three factors has to be 0. So it could be either x squared equals a, which is x is plus or minus root a, two vertical lines. Or it could be y squared equals 1 minus a, which is y equals plus or minus root 1 minus a, two horizontal lines. Or, so I've covered off this one could be 0, this one could be 0, or it could be that thing there is equal to 0. Or x squared plus y squared equals 1, which is a circle centered at the origin, radius equal to 1. Okay, so that's what we've actually got in this picture. We've got two vertical lines, we've got, and this is for all values of a, we've got two horizontal lines, and then we've got the circle. There's a minor detail that we need to cover in this, and we need to prove that there's no gap between the corner of the rectangle and the circle. We need to prove that the corners of the rectangle lie on the circle. It's pretty easy to spot that they do from the picture, but a real quick check of that is to substitute the x value and the y value into the circle equation. Into the circle, and that gives us plus or minus root a all squared plus or minus root 1 minus a all squared, and that when we expand it we get a plus 1 minus a equals 1. So it works, those lines intersect on the circle. Okay, so that's the boundaries talked about. And now we need to find the exact values of a for which the shaded region is half the area of the circle. So to find the shaded area is quite complicated because it's a circle. It's not a circle, sorry, it's 4 segments of a circle. But if we take the full circle and then we remove the rectangle, that gives us a shaded region. So the shaded region is the full circle minus the rectangle. Now the full circle, because it has a radius of 1, the area is equal to pi. And the rectangle has an area of base times height. So thinking about what this rectangle looks like, it's got a base of 2 root a, because the vertical lines are x equals minus root a and positive root a. And therefore the length or the width of it is 2 root a, and the height, the horizontal lines are at plus or minus root 1 minus a, so 2 root 1 minus a is the height of that rectangle. So the area shaded is pi minus 4 square root a1 minus a. Remember, when you multiply two surds together, you get the product of the things underneath the surds. Square root of a times square root b is root ab. So that's it. And then we want this shaded region to equal half the area of the circle. So we're solving this equal to pi over 2. Okay. Find the exact values of a for which the shaded region is half the area of the circle. In other words, the shaded region equals pi over 2. So we have 4 root a 1 minus a is equal to pi over 2. a1 minus a is equal to pi over 8 all squared. A squared minus a plus pi squared over 16, oopsies, not 16, a squared is 64, equals 0. So that's my quadratic equation I need to solve. And if I solve that for a, 1 plus or minus 1 minus 4 pi squared over 64 all over 2. And remember, we're told that a is a value that's between 0 and 1. So working out that value using a calculator and then deciding whether we need to do the positive or negative root. The positive root yields a value of 0.809. And the negative value yields a value of a equals 0.1905. And in fact, both of those actually work, because one gives you a narrow, tall rectangle and the other gives you a wide, short rectangle, but the proportion will still be 50%. Just looking at the error to the question, which we didn't even need, and we didn't need the less than equal to 0 thing to solve the problem. But let's just have a look. This f of xy function, which is equal to x squared minus a, y squared minus 1 plus a, square root 1 minus x squared minus y squared. And this thing here is always positive. But the overall sign of this function depends on the factors, the first two factors. So for it to be positive, we'd need both of these factors to be positive, or both of these factors to be negative. And then if we want it to be negative, they need to be alternating. So the question itself talked about f of xy being less than equal to 0 for various values of a, shaded. So how does f of xy become less than equal to 0? We'd have either x squared minus a is less than 0 and y squared minus 1 plus a is greater than 0, or the opposite. Or x squared minus a is greater than 0 and y squared minus 1 plus a is less than 0. Okay, so the first one, x squared minus a is less than 0, x squared is less than a, x needs to be between negative root a and positive root a, and then this one is y squared is greater than 1 minus a, so y is greater than root 1 minus a, or y is less than negative root 1 minus a. And it's an and, so both those things need to hold. So looking at that, this one here tells us between the vertical lines, and then this one says either above the top one, or this one here says below the bottom one. So in the diagram there, we need to be between the vertical and then above, so that's that region, or below, so that's that region. In both of those cases, that's negative. And if you do a similar argument, you'll find that this is negative and this is negative. So where it says in the question, the shaded regions, the regions where f of x is less than or equal to 0 are shaded, that is correct. And this here where it says positive, that is incorrect. Okay, last part. An ellipse with this equation, x squared over a squared plus y squared over b squared equals 1 is enclosed by the hyperbolas xy equals 1 and xy equals minus 1. Determine the largest area of the ellipse. This is actually a trick question. So the first thing is to work out, oh, that's a terrible hyperbola, that's a little bit better. This is what the curves look like. This one here is y equals 1 over x, and so is that bit. And then this one here is y equals negative 1 over x, and so is that one. A rectangular hyperbola. And then we've got an ellipse centered at the origin that's somehow enclosed in between. My diagram is pretty bad, but the caption, not the caption, the thumbnail for the video is much nicer. And we want to find the area of this ellipse and then find out the area that is biggest, largest area. So I got tripped up by this question myself, because I thought, okay, the largest area is probably just going to be a circle. You know, if I consider a circle in there that's just touching there and there, I did a quick little bit of maths and I thought, okay, well this coordinate's 1, 1, so this will be root 2, 1, 1, and if the area of the ellipse, the area of the circle is needed to be found, then it's just going to be pi r squared, and the radius is root 2, so pi root 2 all squared is 2 pi, and I was like, okay, this is the biggest. And actually that is the answer to the question, but what I just shaded there in green, the ellipse, actually has the same area as the circle, and any ellipse that touches those hyperbola has exactly the same area. They all have an area of 2 pi. So finding the biggest ellipse, there's an infinite number of ellipses that all generate the same area. So we need to prove that, and what we do is we use the discriminant. So we have a circle, x squared plus y squared equals r squared. No, sorry, it's not a circle, it's an ellipse. Turns out the circle is just one particular case. We have this ellipse, and we solve it simultaneously to the hyperbola. And we want to make the discriminant equal to 0, because if it's just enclosed inside those hyperbola, it means that they must be tangent. So x squared over a squared plus, doesn't matter if this is a plus or minus, because when we square it, the signs both become positive. So we've got this equation. If I times everything through by a squared b squared, I get rid of the fractions. And I'm also going to times through by x squared. Now, this is a disguised quadratic equation. If I let something like z equal x squared, then I've got b squared u squared, blah blah blah. Don't really need to make the substitution, I just can solve using the quadratic formula. X squared equals a squared b squared plus or minus a to the 4 b to the 4 minus 4a squared b squared all over 2b squared. And then if we want there to only be a certain number of intersection points, there's only going to be 2 x intersection points. One of them is going to be here and the other one's going to be there, so we only want 2 solutions out of this. Then this dude here needs to be equal to 0, because if it's equal to 0, then we're just going to get x squared equals a squared b squared over 2b squared, which is a squared over 2, and that will give us x equals plus or minus a over root 2, the 2 values of x that we need. So we set the discriminant equal to 0. A to the 4 b to the 4 equals 4a squared b squared. A and b aren't 0, they are the radius in the x and y direction of the hyperbola, so they can't be 0. So we can divide right through by a squared b squared, and we get a squared b squared equals 4. And therefore a, b equals 2. A and b are both positive numbers, so we don't write negative 2 there. And the area of the ellipse is pi ab, so 2 pi. And what that is telling us, and we do need to recognize it, is that the area is constant. Okay, constant for all values of a and b. And this condition here, ab equals 2, is saying if ab doesn't equal 2, then the ellipse and hyperbola don't touch. Okay, they might cross over completely, or they might not even have an intersection point. But AB equals 2 is the condition so that they just touch. And then for that condition to hold, the area of the ellipse is constant no matter what A and B actually are. So we don't need to find the points of intersection, and I was going down on that path. We don't need to find them because we've already found the area. And the area is independent of A and B. Nice little trick question there, the examiner got me. It's funny though, because I had the right answer, but I just didn't have the right logic. See you in the next one.